Good morning to all. Today we are going to discuss the second unit, VLSI fabrication techniques. Okay, so in that we are going to see the first one, CMOS fabrication process. So this is the first topic in this unit. So what is this CMOS fabrication process? You know that from the beginning, that is from step by step evaluation of the chip, how the chip is manufactured from step to step, right? So this is the thing we are going to discuss today. So there are totally 8 marks are available, right? These are the various steps. The first one is creating the envelope process, and the second step is to active areas and field oxide regions, creating active areas and field oxide regions, and third one is forming polysilicon gate, and fourth one is performing the doping operations, the fourth and fifth one, that is N plus doping and P plus doping, and the sixth one is oxide contact, and the seventh level is that metal layer creation, and the eighth layer is that eighth level is that creating vias and higher level metal layers. So these are the 8 steps which are available for the fabrication process. We will see one by one. Okay. So see, this is the first mask, creating the envelope process. Actually we are taking the transistor. First we are taking or identifying the location of the pipettes. Okay. So here in this pipette, adding phosphorus or arsenic to create the envelope regions. Actually the process of adding impurity in the atoms such as arsenic, antimony or phosphorus in the silicon is called as doping. So this is the meaning for doping. The impurities themselves are called as dopants. Okay, that is by adding this arsenic, antimony or phosphorus in this impurity is called as dopants. Okay, and annealing is also required to help the dopants to set correctly into the crystal structures. The annealing means the heating. Ion implantation is known as, that is we are performing the ion implantation here. Okay. So this is the substrate, p-type substrate is taken for creating the envelope process. So here we are creating the field oxide regions, that is photoresistive coating is applied here. So in that we are performing the ion implantation, that is passing the arsenic, antimony or phosphorus for creating the envelope process, right? So the above the photoresistive coating, if you are passing that or if you are performing the ion implantation, a envelope will be created like this. Okay, envelope will be created like this. So this is the structure of the envelope process. Okay, so this is our first level. In second level, we are creating the active areas and FOX. That is, FOX means field oxide regions. Actually, we are having 2 different regions in this, right? That is, the regions of the chips are divided into 2 categories. One is active areas and another one is field regions. The combination of these 2 will be called as, that is active plus field area. Totally will be called as chip surface. Okay. These oxides are formed to provide isolations, right? Actually we want to differentiate one level to the other level or one mask to the other mask. So to create the isolation between 2 layers, we are using these field oxides. Okay. The isolation regions are formed or defined by these active areas of the masks. Okay. So then this mask is actually used to define the FET areas, that is FET regions on the surface by patterning a dual layer of silicon nitride. See, this diagram will explain this. A silicon nitride above that field oxide region, we are giving the silicon nitride surface to provide dual layer isolation. Okay, so we have seen that N-FET structure, that is p-FET structure and envelope process we created in the first step. Above this we gave one silicon nitride layer to provide the isolation in between this. Okay, so this is actually the active area definition. Okay, Actually, we are considering this nitrate layer or silicon dioxide layer is called as glass plate, right? Actually, in between one layer and another layer, there will not be any by seeing that if you are seeing the top layer of the circuit or the chip, the layer by layer, in between that layer we are having isolation layer, that is silicon dioxide layer, in between each layer are having, but it will not be considered because it's considered as a glass plate. Okay, so see, this is the ion implantation, this is subtract etching, right? For giving or inserting the gate, we are etching process will be done, and then that is field oxide deposition, right? So here we are performing the field oxide, that is silicon dioxide layer is performed. Then the third one is after performing that, creating the field oxide regions, we are going to see the third level, that is polysilicon gate. Okay, this polysilicon gate is directed towards forming the actual transistor, right? It is actually the start with the growth of the gate oxide surface. See, above the field oxide regions we are performing the gate oxide. The silicon dioxide layer will be created above this. This is actually called as the isolation layer. Actually here this is MOSFETs are formed using a self-aligned technique. Okay, so where the gate and N plus and P plus regions are automatically aligned to each other. Okay, so see here, this diagram will explain the gate oxide layer. So we have seen that P type substrate, above that we created N-well process, and in active areas we created the gate oxide layer. So above that, by performing the etching, we are inserting the polysilicon gate. Okay, see, in this diagram will explain how the polysilicon gates are inserted in between these layers, right? So in the N-well process, one polysilicon gate is inserted, and here we are inserting one polysilicon gate by etching process. Okay, so the gate is formed by depositing doped silicon on top of the gate oxide and the petaling layer to define the gates. This is the actual formation of this. So then we are going to perform the N plus and P plus doping, right? In side by side of the polysilicon gate, we are going to perform the P plus doping for creating the two regions. So either side of this polysilicon gate will be performing the N plus P plus doping. So this is next steps or ion implants that are used to define the P plus and N plus regions of P FETs and N FETs respectively, right? So for P plus we are creating the P plus regions, and for N FETs we are creating the N plus regions respectively. Okay, the plus designation of P and N type regions is used to imply that the doping density is very large. So that is used to represent the plus regions. Okay, so see, the next diagram will explain how the etching will be created. So then the boron implantation will be performed to create doping. Boron ion implantation will be performed in this polysilicon gate to performing this region. Okay, so this is for creating boron implantation, for P plus implantation, and for N plus doping we are creating arsenic, right? Arsenic is passed to create the N plus region, and for creating P plus regions in this N FET. This is actually P FET and this is N FET. N FET. Sorry. So then the next one is that after P plus doping, oxide contacts, making oxide contacts for this is that how to create the oxide depositions. So then the next layer is that metal contact for the P plus and N plus regions will be created. So then the final one is vias. Vias and higher level metal layers. Actually vias are used to create to make the contact in between metal layer 1 and metal layer 2. So through the vias it can be connected. So that's all about this CMOS fabrication process. Okay, thank you one and all.